Now we're ready to move forward into solving systems of equations algebraically. In this video, we'll focus on systems of equations that are given in function notation. So in the last video, we discussed what it means to be a solution to a system. Remember that if we have some system of equations, which is really just a collection of equations or of functions, then its solution graphically would be the intersection. So on a graph, the solution to a system is the intersection. And remember, this means that we are finding the x and the y value that will be true for both functions or for both equations. When we do this algebraically, we're still asking ourselves the same question, and we're saying, what's the x value that I could plug into this function and it'll return a value here that if I did the same thing in my next function, plugged in that same x value, would return the same value here. So in order to get started on this, what I'm going to do is rewrite my functions as equations. So I'm going to rewrite f of x as y equals 3x minus 8, so from a function to an equation, and I'll do the same thing with my other function. I'll rewrite g of x as y equals negative x plus 8. So remember, the y value and the x value in this top function are the same x and y value that I'm going to end up figuring out in the bottom function. So if this y and this y are actually the same y value, then what I can do is rewrite this as a single variable equation, because y is equal to 3x minus 8 and y is equal to negative x plus 8. Since these are the same y's, then I can conclude from that that 3x minus 8 must be equal to negative x plus 8 because both of these are equal to that same value of y. This is just an application of the transitive property, which says that if A equals B and B equals C, then we can conclude that A must equal C. That's exactly what we're doing here. If y equals 3x minus 8 and y equals negative x plus 8, then those two expressions must also equal each other. So the point of setting it up like this is that now I've got this one variable equation where I can solve for x. So I've got 3x minus 8 equals negative x plus 8, and I'll use algebra to solve. So I'm going to choose to do this first by adding 8 to both sides of my equation. I end up with 3x equals negative x plus 16. Now I will add x to both sides of my equation, and I get 4x equals 16. Finally, I will isolate x by dividing both sides of my equation by 4. I get x equals 4. So that's great, but that's only half of my answer, because if I want to plot the solution on a graph, I can't just have an x value, I need a y value as well. So I know that the intersection, if I had graphed both of these, their intersection would be happening at x equals 4. But what is the y value? What I can do to solve this is plug my x value into one of my equations. And it doesn't matter which one, because after all, they're going to lead to the same solution. And let's prove that. So I could use y equals 3x minus 8, or I could use y equals negative x plus 8. It doesn't matter which one. In either case, what I'm going to do is plug in 4 for x. So I'll do this one on the right first. So y equals 3, I'll plug in a 4, minus 8. 12 minus 8 is 4. I get y equals 4. On the right, I'm going to now double check with my second equation, and if I've done this correctly, I should get y equals 4. So I'll plug in my x value of 4, so negative 4 plus 8, and it checks out because that's equal to 4. So the solution to this system of equations is the ordered pair 4, 4. A solution to a system of equations in two variables is going to be an ordered pair, right? So this, if I were to graph, this is where I would see an intersection, and I can confirm that. In this slide, I have actually graphed both functions. You can see This is g of x. This is the graph. This red line is g of x equals negative x plus 8. This blue one is f of x, 3x minus 8. And you can see that they overlap. Their intersection is right here. And if I look at this ordered pair, it's at x equals 4, y equals 4. So it's indeed at 4, 4. So I've just confirmed that the solution to this system of equations is 4, 4. Let's do another example. So once again, we're going to find the solution to this system algebraically. So the first thing I'm going to do is rewrite both of my functions as equations. To rewrite a function as an equation, all you do is get rid of the function notation and replace it with y. So if y equals 5x plus 5 and y equals negative 2x minus 9, then 5x plus 5 must be equal to negative 2x minus 9. Remember that the whole reason of doing this is to get this down to a one variable equation that we can solve. So I'm going to start off I'll start by adding 2x to both sides of the equation. This gives me 7x plus 5 is equal to negative 9. I'll subtract 5 from both sides of the equation. I get 7x equals negative 14. And finally, I will divide both sides of the equation by 7, and this gives me x equals negative 2. So that's half of my answer. So I can pick f of x or g of x. I can pick one of these functions or one of these equations and plug in an x equals 2 value to figure out what y is. So I'm just going to I'll choose the top one. So I've got y equals 5x plus 5. I'm going to substitute in x, which is negative 2. So I get y equals negative 10 plus 5. So y equals negative 5. And I encourage you to pause the video at this point and do substitution here. Y equals negative 2x minus 9, and confirm that when you plug in a value of negative 2, you end up with a y value of negative 5. So my answer, the solution to this system, would be negative 2, negative 5. Again, my answer is an ordered pair because this is the point where these two lines will intersect. And once again, I have plotted these functions just to kind of show you. So you can see g of x is this line in red, f of x is the line in blue. If I look at their graphs and find the solution, it's right here, and this ordered pair is equal to, let's double check, 1, 2, that's at negative 2, 1, 2, 3, 4, 5. Negative 5, and there should be a negative there. So just as we expected, the solution is at negative 2, negative 5. Let's do one more example. So once again, finding solutions to systems algebraically from function form. So the first thing I'll do is rewrite these as equations. So I'll get y equals 1/3 x minus 7 and y equals 2/3 x minus 10. By the transitive property, I know that if y equals that expression and y equals that expression, then these two expressions must also be equal to each other. So I'm going to rewrite them and use substitute, and that's the substitution part here. I'm substituting, you can think of it as I'm taking this value, since it's equal to y, and I'm substituting it right here. So I get 2/3 x minus 10 equals 1/3 x minus 7. So now I'm going to solve for x. So let's see, what's a good way to start here? I think I'll start by adding 7 to both sides of my equation. I get 2/3 x, and then let's see, negative 10 plus 7 is minus 3. 1/3 x, this cancels out. And then I will have to subtract 2/3 x minus 2/3 x from both sides of my equation. I get negative 3 equals, let's see, 1/3 minus 2/3 is negative 1/3. And let's even double check. So 1/3 minus 2/3, this would be 1 minus 2 is a negative 1. So I get negative 1/3 x. And then finally, I can isolate x. I'll divide both sides of my equation by negative 1/3, or you can think of it as I've got this negative 3 being divided by x. I could rewrite this as this, right? And this is an equivalent expression. So take a moment and just double check that that makes sense to you, that negative 1/3 times x is the same thing as negative x over 3. Okay, so two different ways of thinking about that. And so what I'll do is I will take my denominator, multiply both sides of my equation by that denominator. This cancels out on the right-hand side. Negative 3 times negative 3 is 9. And I get x equals 9. Now that was a little tricky, so this is going to be one of those examples where it's going to be good to double check and plug our x value into both equations and make sure we get the same y value. So let's do that. So we got a value of x equals 9. So if I plug 9 into, let's see, we've got y equals 1/3 x minus 7, and we've also got y equals 2/3 x minus 10. Okay. So let's substitute in our value. So x is equal to 9. So I've got y equals 1/3 9 minus 7. Y equals, okay, so 1/3 of 9 is 3. 3 minus 7, we get negative 4. Let's do the other one. Y equals 2/3. We'll substitute in our 9 minus 10. Y equals 2/3 of 9 is 6. 6 minus 10 is negative 4. So I got y equals negative 4 in both cases. So I can be pretty confident that we've got the right solution, which is 9 comma negative 4. So this is the solution to this system. So again, notice that because this one had fractions, I decided, you know what, I'm going to go ahead and double check and plug in my x value to both equations. In reality, you only need to do it with one to get the answer, but it's always good to double check your work. So this is the solution to this system. And once again, I've confirmed this graphically. So if you look at the graph of these equations, you can see that they overlap. If I look at x equals 9 and y equals negative 4, that's this point right here, and indeed there is an intersection at that point.